Alright, so some thermal physics questions now. January 2018. Convert the time recorded in figure 3b to seconds. That is pretty simple. So that's 5 minutes. So that's 5 times 60. Plus we have 45 more seconds. That is equal to 345 seconds. Calculate the mass of the water evaporated in the experiment. So I think we just look back on that diagram to get the mass. Alright, so our initial mass is 375 grams and we drop to 360. So that is 375 take away 360, that is 15 grams. Next thing now, the power of the electric heater used in the experiment is 100 watts. Assuming no heat was lost to solidness, calculate the specific latent heat of vaporization. So specific latent heat of vaporization, energy equals mass times latent heat. Now we have a mass of 15 grams. Let's convert that to kilograms. So that's 15 divided by 1000, 0.015 kilogram. So all we need now is our energy. Now from our question we have the power. So power is equal to energy over time. Our power is 100 watts, so that is equal to our energy over 345. So our energy is 345 joules. So we're good there now. So just to finish our question now, let me just write it in this space here. Energy equals mass times latent heat. Our energy is 34500 equals our mass is 15 grams times our latent heat. So our latent heat is equal to 2300 joules per kilogram. Or joules per gram, I didn't change it. Joules per gram. So that's it for that question. So let me just erase it now and answer the other questions. In the box below, say the equation that relates big C to little c. So big C is heat capacity. So that's heat capacity equals mass times specific heat capacity. So big C, heat capacity. Small c, specific heat capacity. So distinguish between the two. It's just asking you to define heat capacity and specific heat capacity. You can just Google that. So let's see our next question. A substance which has a melting point of 80 degrees Celsius is cooled from 90 degrees to a complete solid at its melting point. Sketch a graph in figure 1 to represent the statement above. Alright, so we have temperature versus time. So let's just put in our 90 degrees there and start 80 here. So it's cooling. So we're starting at 90 and we're cooling to 80 as a complete solid. Simple 2 marks. Next question now. A physicist converted 2 kilograms of water at 37 degrees Celsius to steam at 100 degrees Celsius. Assuming no heat loss, calculate the amount of energy needed to heat the water to 100 degrees Celsius. So our water starts off at 37 degrees Celsius. Let's just do a quick sketch of what's happening and put that in blue. So we have ice. Now we have water at 37 degrees Celsius. So let's say that's 37. And we go up to 100 degrees. We're still at water. Then at that 100 degrees now we're going to change to steam. So whenever we have a change in temperature, the specific heat capacity, so we use that formula, and when we have a flat part, that's latent heat. So let's do the question now. Alright, so to heat the water to 100 degrees Celsius, that's heat energy equals mass times specific heat capacity times change in temperature. So the heat energy is equal to 2 kilograms times specific heat capacity of water, 4,200, and our change in temperature is 100, take away 37. So that is equal to 529,200 joules. So that is for I. Now to heat the water from 100 degrees Celsius to steam. To get it to steam now, that's mass times latent heat. So our mass is the same, 2 kilogram, and our latent heat of vaporization is 2.3 times 10 to the 6. That is 4,600,000 joules. Now to completely convert the water, this is always just easy marks right here. You just add up everything. So 529,200 plus that is equal to joules. And that's it. So easy marks right there. Next question. Alright, so A, describe how the graph of the volume versus temperature in Celsius of a gas can be used to derive the Kelvin scale. Once again, you can Google that, but the graph would look something like this. Temperature, volume, with negative 273 degrees, that's 0. So this is absolute 0. So the graph would look something like that, and it'll explain how we got that graph. Zero Kelvin is equal to negative 273 degrees Celsius. Alright, so let me start it. A piston traps a mass of gas in a cylinder. At 25 degrees Celsius, the pressure of the gas is 5 atmospheres when its volume is 50 milliliters. Calculate the volume of the gas if the pressure drops to 1 atmosphere at constant temperature. So you should know your gas law formula. P1 V1 over T1 is equal to P2 V2 over T2. Now the question says that the temperature is constant, so these are out of our equations. So we only use pressure and volume. So our initial pressure was what now? 5 atmospheres. So that's times initial volume, 50 milliliter. That is equal to, we need to calculate the volume of the gas. So we're going to find V2 when the pressure drops to 1 times V2. So 5 times 50, that's 250, equals V2. So the new volume is 250 milliliters. After resetting the piston, the gas returns to its initial temperature and initial pressure and volume. So P1 is back to 5, V1 is back to 50. Alright, so now the volume is now fixed. So in our formula, P1 V1 over T1 equals P2 V2 over T2. The volume is now fixed, so we don't use V1 or V2. So that's what our formula reduces to. So after resetting the piston, the gas is if the volume is now fixed and the gas, so what's our initial temperature was 25. So the volume is now fixed and the gas is heated to 60 degrees Celsius. So we know our T2, 60 degrees Celsius. Find the final pressure. So now we have initial pressure, initial temperature, final temperature, and we should find final pressure. Now when you're using a gas law formula, you cannot use anything in degrees Celsius. You must turn the Celsius to Kelvin. So you'll say 25 degrees Celsius plus 273 and we get 298, and our other temperature 60 degrees Celsius plus 273, that is 333. So now we'll just put everything in our formula now. So P1 is 5 over T1 298, that is equal to P2, which we are finding, over 333. Let me make some space here. So now this reduces to 1665 equals 298 P. So our pressure is equal to 5.59 atmosphere ATM. So that's it for that question. Alright, so this is another paper, define specific heat capacity. Just Google that. SI unit of heat capacity, that's joules per Kelvin. Specific latent heat of fusion, symbol is L, little f. Symbol for gas law, P1 V1 over T1 equals P2 V2 or T2. So anything with 1, so P1, that's initial pressure. Anything with 2, that's the final pressure. So we have initial pressure, initial volume, initial temperature, final pressure, final volume, final temperature. A physicist converts 8 kilograms of water at 33 degrees Celsius to steam at 100 degrees Celsius, assuming no heat loss. We did a question like this before, so you can try this one. SI unit of specific heat capacity, that's joules per kilogram per Kelvin. Specific latent heat of vaporization, that's LV, and that's joules per kilogram. Define heat capacity of a substance, just Google that, but it's the amount of energy needed to raise a substance by 1 degree Celsius or 1 degree Kelvin. Symbol is just, that is the equation that links heat capacity to specific heat capacity. The housewife left 25 grams of ice in an open insulated container while she's answering her cell phone. When she returned, the ice at 0 degrees Celsius was converted to water at 3 degrees Celsius. Calculate heat energy needed to totally melt the ice and reach its present temperature. Alright, so we had ice at 25 grams of ice. So let's change that to kilograms. So 25 divided by 1,000. 0.025. So that's our mass. So we're raising the ice, changing the ice to water. So that's first we use latent heat. So for the first part, let me just get a quick sketch here. We have ice at 0. We're going to get water at 0. Then we're going to raise that water to 3 degrees. So we don't just jump from ice, 0 degree ice, to water at 3 degrees. We have to change it from ice to water, then raise the temperature. So let's say that part is A, that part is B. So to do A, changing ice to water, that's heat energy equals mass times latent heat of fusion. So the mass is 0.025 kilogram. The mass is 0.025 kilogram times the latent heat of vapor of fusion of ice is 4000. Running out of space. So the mass is 0.025 times latent heat of vapor of fusion of ice. And we get 8,500 joules. Now for the second part, now it's a raised temperature of the ice, so that's heat energy equals mass times specific heat capacity of the water times the change in temperature. So the mass is the same, 0.025. Specific heat capacity is 4,200. And our change in temperature is 3, because we change it from 0 degrees Celsius to 3 degrees Celsius. And we get 315 joules. So all we need to do now is add A plus B. So to get our final answer now, we add them both, so that's 8,500 plus 315, so that's 8,815 joules. Now if this melting and heating activity took place over 300 seconds, calculate the rate which the ice or the water was receiving heat. So 300 seconds. So the ice and the water got 8,815 joules of energy in 300 seconds. So that's approximately 29.4 joules per second. That's it for that. CSEC Physics teacher gave 2 groups of students projects on specific heat capacity. One group used an electrical method to calculate the specific heat capacity of a metal block. We have a circuit set up above. Describe the method. You can Google specific heat capacity of a metal, electrical method, because you also have the method of mixtures. For this question 6a, you can just Google this method. Just Google method of mixture specific latent heat of fusion of ice. Now part B. A physics student was provided with 25 grams of ice to convert to steam. How much heat is needed to change this 25 grams of ice at 0 degrees Celsius to steam at 100 degrees Celsius? So let's draw a map of it. Looks like this. Say 100 degrees there, 0 degrees here. We have ice, so we get the ice to water first, then we raise the water to 100 degrees Celsius, then we change that to steam. So we need to know our parts. So A, B, C. Now on our graphs, anywhere that's flat, that's A and C. We're changing state, so that's heat specific latent heat. And where there's a change in temperature, that's specific heat capacity. So for part A, let me section this up. A, B, C. So for part A, we're changing, where is it, latent heat, so EH. Part B, heat capacity. And part C. Alright, so now our mass is equal to 25 grams, that is 0.025 kilogram. So 0.025 times our latent heat of fusion of ice, 3.4 times 10 to the 5th. So that is 8,500. Part B, our mass 0.025 times specific heat capacity, that's 4.2 times 10 to the third, and our change in temperature is from 0 to 100, so that's 100. That is equal to 10,500. And our final part now, our mass is the same, 0.025, and our latent heat of vaporization this time, 2.3 times 10 to the 6, 57,500. Now, so our final answer is just A plus B plus C, which is equal to 8,500 plus 10,500 plus 57,500. 76,500 joules. Alright, question 5, state the equation for the general gas law. That's simple. P1 V1 over T1 is equal to P2 V2 over T2. Now this is a girl group of balloon during a Christmas celebration. In terms of the kinetic theory, how pressure is exact. Okay, you can just Google that. That's quite simple. Just Google the kinetic theory and you'll see the answer. So let's go on to the next part of question 5. That's something you can just remember, so there's no need to write it here, and you can just read it on Google. Alright, a block of ice of mass 2000 grams was heated from 0 degrees Celsius to steam at 100 degrees Celsius. Calculate the energy in joules. Alright, so let's just do a little map here. We have ice at 0 degrees Celsius here, so that's ice, and we're heating that to steam. So when we add heat to this ice, it changes to water. So as time progresses, there's no change in temperature because it's changing energy. Then we go up to the 100 degrees Celsius, that's still water, and then at the 100 degrees Celsius, it changes to steam. So here where we have the flat part, it's latent heat, so that's mass times latent heat. Flat part, mass times latent heat. And we have a change in temperature, that's specific heat capacity, little c. So let's name this now A, B, and C. So let's calculate A. The mass of the ice is in grams, so let's change that to kilograms. So 2000 divided by 1000, so that's 2 kg. So our mass now is, for part A, it's 2 times our latent heat of fusion of ice is 330,000, that is equal to 660,000. So that's part A. Part B, EH equals MC delta temperature. So the mass is 2, specific heat capacity 4,200, and our change in temperature is 100. So that gives us 820,000. Now for part C, our mass is the same, 2 kilograms, and our latent heat of vaporization is 225,000. So after we calculate that now, we add everything. So that is 450,000. So now we need to add A plus B plus C. So that is equal to 660 plus 8. And we get 1930. And its energy, so that's joules. So that's for the first part of the question. Let's separate that. So this is for up there. Now, so the second part of the question, so that's in a different color. If the activity took place over 6,000 seconds, how much power was utilized? So power is equal to energy over time. So our energy, our power is equal to 1930 0.0000 over 6,000. Zeros cancel. So we have 1930 divided by 6. And we get approximately 321.6, so reoccurring 6 joules per second. That is 9 marks.